I think we can start. It's 11 now.
Okay.
All right. We have Stephen Edwards here today from Columbia. We have collaborated before, never met before. So I'm very excited that you are here. You will talk about the sparse synchronous model, and I will just leave the floor to you.
Okay, very good. Thanks much. Let's see. So yeah, this is like a 4-year story of stuff that I and others have been working on. Let's see. So that is. There we go. Okay. So what I'm going to talk about is real-time software, and in particular, the idea is that the time at which something is computed is as important as the value. So 1 + 1 is still 2, but you want to say more like, I want to know 1 + 1 at exactly this time, and that is just as important. Now, broadly, it's going to look something like this. We're going to take in events from the outside world, think of them as inputs on GPIO pins or something like that. Ultimately, we're going to timestamp each one of those. The input change to 1, 0, 0 time, or input change to 0, 1, 1 at time 5, and then change again to 1, 0, 0 at time 7. So all of this information gets fed into our program here, and I'll talk much more about what goes into this box. And one of the things it generates going out are time-stamped outputs that similarly will come out with precisely timed stuff. Furthermore, the goal here is to implement this on resource-constrained microcontrollers. One of my favorites, this is the Raspberry Pi Pico, is this RP2040 chip on it, which you can buy the chip in quantity 1 for $1. The board itself, I don't know, it's like 5 or 4, depending on how many hundreds you buy. I don't know, Leonard, you remember how much the little tiny one was?
No, I mean, it was 10. Maybe.
Yeah.
5.
Yeah.
What else is on the board?
Not much. So it's mostly the chip. This, I believe, is the serial flash. You've got some, the usual power stuff, say crystal and so forth. Almost nothing. A couple of buttons. These all are just pins going straight to the chip. So there's not much on this board, but it's fancy enough. So it's got a USB connector on it. It has firmware on it where you program the flash by plugging this thing in. Looks like a flash drive. You drag the file into it and it goes. But all those things are fun. The really cool thing it has is weird hardware that will support input and output stuff like this. And we'll get to that later.
So in the things on the left
Yeah.
there, what happens if the bottom one changes up and down in between 5 and 7?
Oh, then we would get another.
You get more.
Yeah. With the idea here is that anytime any of them change,
Okay.
I've somewhat artificially put this together, assuming that these are all truly simultaneous. Practically, maybe that'll happen, maybe it won't.
But they are sampled on a clock edge.
They are sampled on a clock edge. But let's see, I managed to get that clock edge up to 60 megahertz. So it's going reasonably fast. Yes, please interrupt me. I much prefer dialogues than monologues. It reminds me that you guys are still alive. Okay. Was it 4 years ago now, maybe 5? John Way and I sat down and came up with a series of axioms that we want for this model. There are a number of sort of real-time models out there. I'm most familiar with the synchronous ones, Estros, stuff like that. And also with the tides model that my PhD advisor had developed. And I wasn't satisfied with any. So of course I decided to create a new one. The key thing is that time exists as a first-class object in this world, in this language, in terms of seconds. And you can, if you have 2 times, you can subtract them, you can add one to the other, divide, multiply, do all of that stuff. But in particular, it's you can speak of it arithmetically. So this is very different than a lot of the synchronous languages that has the notion of, well, the previous sample and the next sample, but that's kind of it, right? I mean, you can count cycles, but then you're required to do that yourself. Okay, this is another sort of key thing. So time is quantized. Now, I'm not going to tell you what the quantum is, and let's see, I think there actually is a way to leave that information to the user. But the idea is the user shouldn't know what that is. The user should just be able to say, give me this many microseconds, and the system does the right thing. Now, practically, the quantum that we managed to get up to is 62 and a half nanoseconds, which is 60 megahertz worth. What I wanted to do was have integer timestamps that we could actually measure. So in particular, no floats, not attempting to fake real number. The other goal was to thwart xeno behavior. So if you keep taking a time, dividing it by 2, and dividing it by 2, at some point it'll magically turn into 0, and dividing by 2 is not going to do much more. Okay. Here's where the synchronous part comes from. So this is a key engineering assumption that is, of course, unrealistic, but you can fake it. So the program thinks it's running on an infinitely fast processor. So in particular, if you've got a sequence of instructions that run in an instant, they will all think they're running at exactly the same instant. So if they all look at their watch, they will see exactly the same timestamp on it. And of course, that's physically impossible, but you can easily come up with a simulation environment that presents that fiction to the software. The reason for that is to make it easy to reason about what the software sees and what it controls. So in particular, 0 plus 0 is still 0, so you can step through these things fairly quickly. If you want a delay, you have to ask for it explicitly, but then you're saying, oh, this number of seconds or whatever. The goal of the runtime then is to try to maintain this fiction as much as possible. The equivalent is in synchronous digital logic. We don't really think in terms of, well, this NAND gate takes this many picoseconds and that one that takes that many picoseconds. We think about, okay, we've got this work to do in a cycle, and we're going to make that happen. Later, you go to make sure that you can run the clock at that speed. But when you're doing the functional design, you don't count the picoseconds.
Is it the same here that you have to fix things afterwards when it didn't fit into?
Yeah, so that is the scheduling question. So it's, once you've written a model, can you actually execute it on the hardware that you have to build? And to decide that, I don't have a really good answer for that. You'd have to do, worst case execution analysis or something like that. And I've not done that. What is interesting is if you give it a bunch of events suddenly and it gets behind, it actually does a pretty good job catching up later. Now, of course, if you bombard it constantly with events, you can stymie the thing. It'll eventually fail, or it'll get so behind that it's absurd. But one of the neat things about this is that if it misses a deadline, it's able to catch up, and the program doesn't go really crazy when that happens. So it's a nice program. Okay, so synchronous is things take truly zero time. Sparse is in most of these instances, nothing happens. And so the idea is that we're sort of asking for the impossible, get instructions to run in zero time, but we're going to do that by saying, okay, well, all of these things pile up at 100 milliseconds, but if you don't do anything for a while, I can then do the next batch exactly what I've asked, even though there may not be enough time. Yeah.
So you are seeing that sometimes it gets overwhelmed and catches up.
Yes.
Right. But like I was under the impression that these kind of systems were like usually very timing critical.
Right.
So is that a problem or not?
Right. So the what to do if you get behind question is a very interesting one that I've not really addressed. So one of the things we could do is put in something that says, oh, you've fallen so far behind, it's an error condition, you should go and do something about it, or something like that. Certainly you would also like to prove that, oh, you're behind, or something like that. Again, I don't have a really good answer for that at the moment. But practically, I've built plenty of systems where, in fact, it does very consistently always meet deadlines. So,
but it means that the output could come later. You turn off the X-ray cannon too late.
yes, yeah. No, there's certainly a danger of that. And if you're going to be using this as an X-ray cannon, you definitely want to do a bunch of additional analysis to make sure that it's going to work.
So can I
Yeah.
say something? So it's not the intended behavior that when you get behind, you can catch up, and so the programmer says, well, I don't care really if I get behind because I will catch up later on. That's not. I mean, this is like you're not supposed to get behind, but if you get behind, this model has a possibility of catching up later.
Yeah,
Right.
yeah, exactly. It's that, okay, yes, bad things can happen, but they don't take down the whole system, and it sort of recovers reasonably. And we've experimented with this a bit. It's sort of frequently when we were playing with it with experiments to sort of try to break it. And so we were very pleased to say, okay, yeah, we can kind of break it and we can see it breaking. But then when we backed off a little bit, it kind of went back to behaving itself properly. So yeah, specifically with the X-ray ray gun, there's certain things that we could probably be very, very cautious about and make sure that would happen, but in other cases, not so much. Yeah, John?
So the deadlines are not absolute.
Yes.
That means that, no doubt, some are more important than others. For example, the X-ray ray gun may
Right,
be
yes.
the most important one.
Mhm.
There may be other deadlines that you would rather miss
Yeah.
if you have to choose between them. So given that you are, you're trying to do something sensible when an overload happens,
Right, yeah.
does it make sense to have some kind of priorities or some strategy
That's-
for making those decisions?
That's a phenomenal idea and not one that I've experimented with particularly. It then becomes a tricky thing of sorting out what having the programmer decide what the priorities are and then how to deal with that. A step back from that I actually want to talk with all of you about in more detail, and say I don't have an answer, but I've got some good ideas. Is more can you do earlier deadline first schedule, right? If you have a bunch of things that you need to be working on, and this one's due in a millisecond, this one's done in 100 millisecond, do the millisecond one first, and then fuss about the 100 millisecond one. At the moment, I'm not even distinguishing between that, although I do have that information somehow. But how to exactly bring that in is not quite so clear. But yeah, that's an excellent idea as well. Okay, here's the hello world of this world. It's just blink the light at 100 millisecond period. So the way it works, so this is this funny language that we've come up with, slang for sparse synchronous language. It's very much Haskell inspired. Everything is a do block. It's meant to be functional, but LED here, for example, is a mutable variable, meaning that you can schedule updates on it in the future. And so this guy is somehow connected up to the LED on the board to make it blink. Let's see. So when execution starts, it's at time 0. Arbitrarily assume that the LED is 0 at that time. Loop is an infinite loop. After you give it a time, and the functional folks will guess the trick I'm coming here for. MS is actually a function that takes its argument, multiplies by whatever the magical number is, and returns the time in quanta, but doesn't tell you what that is. This is saying schedule a future update of the LED to do this. And so the rule here is evaluate this expression right now, figure out what that is. This is go figure out what the current value of LED is 0, invert it, schedule an update for that 50 milliseconds in the future. And even though it took some time to enter this thing and enter the loop and start running after 50, all the rest of it, all of these things see the same 0 time on their clock. So as a result, the update is scheduled for absolutely precisely 50 milliseconds on updating. Then the other key thing is being able to wait on one of these variables. And the idea is that this is pause the execution of whatever thread you're in and resume it in the instant in which this variable is written. Now, it doesn't necessarily need to be updated. It's just looking for a write. So if you write the same variable to it, you can wake it up. And that's useful because then you can use unit or void to represent just a pure event where the value doesn't matter. It's just, set that something to it. Okay, so at this point, the program suspends. time elapses. And at 50 milliseconds, we put the update into an event queue, and it knows, okay, well, we're now at 50 milliseconds, let's update the value of that variable. That wakes up the wait instruction, sends it around the loop, tells it to schedule the next one. And even though, of course, it takes time for the thing to be, for the wait to wake up and for it to go around the loop and the after to execute, because it's synchronous, everything sees the same time. So the result is that when this thing schedules the next update, it sees it scheduled it to exactly 100 milliseconds. And again, this is regardless of how fast the processor is actually going. And so forth. And so the result is that you can find programs that look like this in just about every little, real-time startup thing, Arduino or what have you. And they look like they work, and when they run it, it works. But if you actually put a crystal on it, you discover no. The delay is at least this amount because it doesn't account for the time that the execution takes going around the loop. By saying it's synchronous, and that's really just tricking it into time doesn't advance, that problem goes away. So that's the key idea. Yeah.
I don't understand what the wait is.
Ah. Okay, so back here at time 0, we schedule an update to LED at 50 milliseconds in the future. Then we execute this wait instruction. Wait says block, do nothing, pause the execution of this program until something writes to this variable.
Okay, yeah.
And it's going to be exactly this update.
Yeah.
So it's a very low level thing, and in fact, one of the goals of all of this is to use very low level. I mean, this is a very awkward thing. Schedule something to be updated in the future and wait for it. But the idea is that you can write functions that then encapsulate these things and build fancier abstractions on top of it. This is really
And you can have multiple of these, I guess. It's not just a single
absolutely
loop.
Yeah. So yes, one thing you can do is you can say wait on multiple variables.
No, I meant,
Yeah.
I can have 2 blinks running at the same time.
Yeah, absolutely. In fact, that's the next slide.
Okay.
So I had a question about the after thing.
Yeah.
And it's the syntax that I'm not quite clear about. Is this whole thing one construct?
Yeah.
After 50 milliseconds,
Yes.
update led?
Yeah.
Or could I put a wider selection of things after the after?
Let's see.
For example, several assignments.
Yeah. So this is a ternary operator, ternary operator after
Okay.
comma and assigned to.
Okay.
So this, of course, could be arbitrarily complicated, but at the moment, it's scheduling an update to a variable at a time. And it's variable time new value,
And only one variable.
and only one variable.
So all updates are at a later time.
There is a version where you could just say immediately lead gets not deref lead, and that will also happen as well. And that's effectively saying now do that assignment.
But in the next instant.
No,
Okay.
it's in the current instant. And so if there was something else waiting on that LED that could see that in the same instant, it would pick it up.
So the ordering of events within an instant does matter.
Yes, absolutely.
If I'd said after millisecond 0, does that happen in the same event?
Yeah,
or
I
the
think
next?
it short circuits it, so it's equivalent to that.
But if you do the loop, then it would just hang and.
No,
Back in.
because let's see, I think wait says wait in the future.
Oh, that's what I meant.
For
Okay,
update.
right.
Yeah.
So, okay, so
So I think it's
the
okay.
assignment happens in this instant, but anyone who's waiting for it will be woken up in the next instant.
No, it's well. If someone is waiting for it in the current instant, it'll be awakened. But when you execute wait, you don't wait in the current instant, you wait in you wait for
I
a
see,
future
yes.
instant.
Right, yeah.
So I think it does work. Let me answer Leonard's question. So actually, so there's two key takeaways I want you to get out of all of this. One is the whole, it's a useful fiction to present to a program that it doesn't take any time to execute unless you specifically ask for it. And this is a really powerful thing to let you glue things together and reason about what's happening. The other key thing, and this is actually the mistake that a lot of these environments fail to make, is that you need different rules for what happens within an instant than rules that happen between instants. So if any of you are familiar with this kind of low level stuff is exactly what you would find in Verilog or VHDL or another discrete event simulation environment. The key mistake I think they make is that they try to use the same machinery to handle concurrent events as events across time. And it's exactly these kinds of issues that you talked about. You know, what about these corner cases of zeros and all the rest of it? And most other discrete event languages say it does what it does, and don't write it that way or something like that. And this is something that came from the synchronous languages community. No, think really carefully about what happens in that zero instant, because if you don't, it's going to come back and bite you. So to address Leonard's concern and also what I just mentioned, the whole other thing I wanted to add to all of this is concurrency. It's a pretty simple thing to think about single threaded, but the whole point is, you know, how do you do multiple things? So to solve this problem, to answer the question, what are the order of things within an instant? I use a pretty simple mechanical, a pretty simple rule, which is concurrent stuff executes in syntactic order. So let me give you an example of that. So here's a little function that has a side effect that says go and get the current value of whatever x is, add 2 to it, and then write into it. And so this is an instantaneous thing. And this is look at the value in the current instant and write it in the current instant.
And if you deref again after that, then it will have the new
It
value.
would see the new value, right? And there's absolutely the notion of after that in the same instant. Well, let's see, and then similarly multiply by 4. So I chose these to be non-commutative operations specifically because it's, you know, the order in which you operate is going to cause problems. So you know, here you go. Here's a little program. Let's allocate a 1 as one of these mutable variables, and then par. People have complained about par isn't really par. Maybe it should be height or fork or something like that. And it certainly is its own weird thing. But practically, what you do is you give it a sequence of things that are all started up in parallel. Now, here they're really boring because they terminate instantly. But the rule is that in one of these par things, this guy gets to go first, and then that thing. So the result is that you run this thing, and you will absolutely, if you deref A at this point, you will get 12.
So it's more like seek.
It's almost like seek, yes. The difference is that this doesn't have to execute determination. This doesn't have to execute determination. So this thing could wait, that thing can wait.
When does the par as a whole terminate?
Say again?
When does the whole?
Oh,
terminate?
when all of the branches terminate.
When you say wait, you mean wait to another time instance?
Yes,
Okay.
yeah, exactly. So I'll show you an example in another slide where this is blinked at 1 rate, this is blinked at 1 rate. It does the rate thing.
So if there were somebody already waiting for an update to A, then run
Well-
here it's syntactically earlier.
Right.
Then it would run between the and2 and the mod 4.
So if you put something else up here that was saying wait on A, it actually wouldn't see these because those instantaneous updates happen later in the same instant.
But if you had something up there that had run at a previous time and was already waiting.
And was already waiting, yes, then it could separate. No, because like I say, it's always a syntactic thing. So what I could have done is say, wait for a while and then do add A, wait for a while, then do mult 4, then wait for A here.
Right.
And then when these guys update, this thing would have seen it and would wake up and run, if that makes sense.
So is it not allowed to wait for A in a syntactically earlier position?
Oh, no, you can, it's just that you won't see updates from it done later in your instant.
Do you see it in the next instance or?
You don't see them in the next instant. What I could do is I could change these afters so that it would fire it and it would see it.
So if you had add one thing to the par, the first thing is wait A,
Right,
and then add 2A and then multiply 4A.
right, right.
So when would that,
It would miss it, it would never see it.
it would never see it?
Yeah, because it would go in and start waiting. Then you'd have the updates to A, but it's already had its chance to run that instant, and so it would miss it.
Poor guy.
Yeah. It's a strange thing, but in fact, you're right, it's almost more like seek or pipeline. In particular, information in one instance can't travel backwards.
So that means that wait. It's
Yeah, but
it's never gonna.
Yeah, that way would deadlock, effectively. So, yeah,
And so if you do two pars, like an outer par
yeah.
that starts a wait on A
Mm-hmm,
and then schedules that second par after some time,
mm-hmm.
then could the wake up between the two operations?
So it's the order in which that outer par fires off the other things. And the answer is no. The way we've got it at the moment, you don't get to sort of insert something here a posteriori. You have to sort of decide what the data flow stuff is.
So that means the wait on reference never works if it appears syntactically before you
Yes.
update to that reference.
If it appears syntactically before, and all you do are instantaneous updates to it. If I said here, after millisecond 50, update A, and then update here, I would say wait A,
Yeah, okay.
it would catch it.
Yes.
Because this is saying, oh, well, sort of at the beginning of this later 50 millisecond instant, it would pick up.
So there's some language that distinguishes if you do after 0 or do it now, so that you say, I don't remember which one, but if you do this or corresponds to after 0, then
VHDL would do that.
yeah, then it won't
Yeah.
fire in, but sort of when everything else in this time
Right,
instead
right.
has run.
Right, yeah, and the problem with VHDL, and the problem with most of these things is that you can very quickly get non-determinism. So you guys are perhaps rightly concerned that, oh my God, this particular statement never gets a chance to run. I'm much more concerned about, wait, all of these guys will run, but I don't know the order. Yeah,
So does it make sense to separate the variables into two kind of variables, ones that you can update instantaneously and ones that you can only update in the future? Because waiting on the ones that you update in the future, that makes sense. Waiting for the ones that you update instantaneously, does that make sense?
yeah, no, that's a good point. So. That's a very good point. So. You're right, I may have conflated those things a little bit. What I actually have in our slang language are immutable things like this pointer. And mutable things like this value. And the mutable things, not only can you change them, but you can schedule updates in the future. It's possible, I'm not sure whether it makes sense or not, or how helpful it would be, but you're right, you could have additional flavors of it saying, oh, you can have a mutable variable that you can't update in the future. And then say, oh, if you have a schedulable variable that you can update in the future, you can't say after 0 or something like that. The idea was this is meant to behave much more like mutable variables assignment in normal imperative programs, where the weight is a little sort of there's no real equivalent to that in normal.
Well, you can use those to communicate downwards.
Yes.
When you want to communicate upwards, you have to use a
Right.
schedule variable.
Well, yeah, and then you have to do a delay or something like that.
presumably the time after is an expression, and so
Yes,
in some occurrences it might be 0 and in others it might not be.
yes, yeah, so you could come up with weird cases where, oh, it'll catch this one, but it won't catch that one, yeah.
What happens if I say after 1 picosecond?
So that will work. And well, it depends. If that's smaller than the quantum, then it will treat it as 0 and be kind of annoying. But
That sounds dangerous.
yes, yeah, it's a little dangerous, but we're talking about picoseconds in a software.
Yeah, but I don't, since you don't tell me what the quantum is,
Right.
I can't know.
There's some asymmetry there. No, that's a very good point. And maybe what I should do is have a ceiling, use a ceiling function instead of the truncation function for the times. That's an interesting point.
But then you will be automatically late. If
Oh,
you divide.
If you say do it in a picosecond, you're automatically.
But if you do it, if you say do it in 117 picoseconds, you
Right,
may still be in time, but since you truncate upwards, you will not be in time. So you should only truncate upwards when you round to 0.
possibly.
I know.
Yeah, okay, there may be some rules there.
Maybe that you shouldn't allow after 0.
Yeah.
Well, the question is, should I prohibit this then?
Well, no, that's different.
No, that doesn't say after 0.
It
Doesn't- They would be different if you didn't allow after
Oh.
0.
Yeah, well,
Yeah, if
Yeah.
you treat after 0 like epsilon updates in a VHDL.
right, and that's exactly where you get in trouble with the epsilon updates, is that you lose ordering with that really quickly. And so this
You
is,
can get arbitrary many epsilon updates.
you can get arbitrary
Yeah.
many epsilon updates, and you can easily create things where you can't determine the order in which they operate. And because you have that plus mutability in parallel with HDL, I absolutely refuse to do epsilon updates because they're very undisciplined.
So if you write after n, then when n is positive, that behaves in quite a different way from after 0, the way that you described it. And I just imagine as a programmer, it'd be very easy to forget the 0 case and to write code that doesn't work. So I think it might actually be a benefit for the programmer just to raise an exception at that point. And
Yeah,
say,
yeah.
You thought you were waiting here, but
Yeah.
you're not.
Yeah, that's not a bad idea. Another thing that's of even more practical use is to be able to say, after at least this time, do this, or something like that. And in particular, you give it both a time delay and a guaranteed lower bound on it. And you can either throw an exception if you go under, or just say, oh, well, it's less than that, we're gonna set it to that. And that would solve your 1 picosecond issue.
I mean, I would like to be able to say, run this as soon as you can, but in a different time step. So if I have a computation that's very long and I need to sort of pipeline it, I want to be able to say, well, run a bit now, and then as soon as you can, run more, but I'll give you a chance to schedule in between here.
Right. Well, and so this is, to me, the really big question. And I don't have a good answer for that. And this is one of the things I'm talking about. At the moment, the way it's done is this is executed to completion at time 0 or whenever this after runs. But that's more aggressive than it needs to be.
Oh, you're running the expression at time.
Yeah.
And at
Yeah.
time now.
Yeah, because in particular here, I'm referring to the value of LED now. Whereas there might be a bunch of stuff that you can guarantee won't change between now and 50 milliseconds from now. And that would be the thing to sort of put here. It's, if this were a long running process, you would want to say, well, okay, make sure you've got it ready by 50 milliseconds, but I don't care exactly between now and 50 milliseconds when you do that computation. But again, I've not figured out the magical way to schedule it to make that work. It's particularly tricky because when what you don't want to do is let that happen if LED could bounce around between now and 50 milliseconds and have it see a different value. You don't want that. You want it,
But what if you do want that?
well, if you do want that, then there's a different way to write that. You write some weight or something like that. No, tell me the value of whatever you want. But
I think the more magic you do, the less easy it becomes to reason about things. That, I mean, this is very simple and easy to understand. Like I compute it now and I schedule the value for later. if you want to do magic, then how do you?
Well, so you want to do scheduling magic. You don't want to do semantic magic.
No, right?
You
but-
want to be able to, you want to be able to
No, I
reason
meant
about it.
scheduling magic, because you don't want to know when you write the program, you want to know this is gonna execute in time. But when you do scheduling magic, you don't know if you're still doing other things that you don't, because you may still be computing something that you think you have already computed because it looks like you've already computed. This makes it clear when it's computed and when you pay for it in time wise.
Yeah,
now.
I disagree, because there are all kinds of funky things going on in scheduling at the moment, right? The whole synchronous thing is of course live, right? This is.
Yeah,
But we at least sort of agree, oh, it's, you know, we're doing these things in the right order in the particular time. To make that work.
So we're assuming there is only one core, right?
Yes, so this is actually a problem. The way I've got it set up at the moment, I don't know how to do true parallelism, right? Because of how I'm doing this stuff. Here, I know they don't commute, but that's okay. Par assumes these don't commute and says this one and that one, thank you very much. But if you had some way to know that these two things could commute, then you could consider doing true parallelism, running multiple cores and so forth. But I don't know, Leonard, can you put an extension into Haskell that would say if there were some updates to whether it would commute or not? I'm kidding, that's nearly impossible. But that's what I thought. Yeah. Okay. Yeah, sounds good. Anyway, the other punchline is that yes, this is, if you do it the other opposite order, you'll get a very different answer at the end. But again, it's well defined, at least.
Yeah, don't call it par.
Okay. Okay.
But it is par if those tasks contain weight.
Yeah.
Yes, but yeah,
Yeah. So this is an example of this. So this is doing almost the same thing. This is going to give it the LED and the period to blink. Here I'm doing something a little bit different. Instead of waiting on the LED, I'm waiting on a timer thing that I've created. This is unit or void or something like that. So this is a pure events. This is weird notation, but it kind of works. But it's just exactly update this time in the future, pause on it, wait until the loop. So it's doing exactly the blinking you expect. This is closer to par because these things will in fact be blinking the same LED at these 3 different rates. And sure enough, I think, well, at least at 6,600, there may be some different times where it happens, but all 3 of these are gonna fire and they will do it in a very particular way and it will turn off the LED, turn on, turn it off.
this
Right.
might not blink the way I thought it would blink. I mean, now I know, you've told me that you
Yeah.
compute the new value to assign to LED and the current time step. But if I wanted to sort of invert the LED,
Oh, but that's what it's doing here.
well, it's inverting what it is now,
Right.
not what it is in 50 milliseconds.
Yes. Yeah, and so the result is that when you put these things together, if you've got 2 edges coincident, they will cancel each other out. And you won't see that blink. Does that make sense? Or is that?
No, I mean, I understand what this is
Okay.
doing, I think.
Mhm.
But I would like, if I didn't, well, you said there was another way if I wanted something different.
Yeah. Something like that, yeah,
So if I set up 2 blinks with the same period,
yes.
nothing will
will it
happen.
blink or not blink? Because I think, like, my understanding is that it would blink.
Let's see.
Yeah,
So,
it
yes,
would-
2 of these with exactly the same period.
It would blink.
Because
No.
you sample.
Yeah, no, I don't think it would,
No.
because
Why?
you run 2 of these.
Yeah,
Yeah, but they sample in the current.
they both sample 0 in the first time step and schedule an update for 1 50 milliseconds later.
Right, but at this, and in the same instant, they also look at current LED and they would see this update.
Remember that
No.
instantaneous updates you see, the
But
later ones.
This is not scheduling the update.
Oh,
for
it's
the
not?
future. This is
Oh,
doing
yeah,
it-
oh, yeah,
This is a
okay,
little different.
it's the time, yeah.
Ah.
If we had the previous one,
Yeah,
then,
the previous one would do something different.
Yeah,
This is literally.
Yeah, this-
This is toggle whatever LED value you see at that time.
yes.
You're right, that is different.
No, I'm confused now.
Say that,
I'm confused.
okay?
I'm saying, oh,
It's an
right, after
instant,
wait, right, I see, it's toggle.
it's
Yes,
toggling
yeah,
now, it's
So I'm
toggling now.
I'm playing a different game, so I'm not waiting on LED.
yeah.
I'm waiting on these timers, and
Yeah.
each of them are independent.
Just another observation. After a loop, there's
Yes.
no point writing anything, right?
So
Because the loop never terminates.
loop never terminates.
So there's no point writing anything after the loop.
That's correct.
It would be nice to get an error from the compiler if you did that.
That's a good point.
And in the same way, there's no point writing anything after this part. Because that will
Yes, because we know that they won't turn. You're right.
Yeah, does
That's
your
correct.
compiler do that?
I'm not doing that checking for the moment.
But the parsings could terminate, it just
No.
happened.
Yeah, in general.
In general, not
Oh,
in
in general,
general.
yeah.
This is fine.
Yeah,
But yes, yeah, in the case where we know that, at least one of these will never
There's
terminate.
really two different parts.
what?
No, it's just that here it's looking for termination and we know will never happen.
Hmm.
But no, I've not done are we trivially deciding that it won't? Part of that is I keep thinking, well, exceptions would be an interesting thing to add, but I've not added. It's really fussy.
Don't,
But that's okay. Sorry, I don't. Okay. yeah. Okay, so, that is the formalism, and this is the slang language I've been talking about. So what I want to do is talk a little bit about the journey that we've gone through to get there, and some of the things we've done along the way.
you know that there is another slang language,
With two S's,
no,
we search. Okay, so 2020, we presented the C API and the SSM runtime and the semantics that we talked about. And we presented sort of a prototypical syntax, a bit like what I showed you there. We actually have a compiler now and so forth. The basic trick is two priority queues. There's one with timestamps in it for updating variables in the future. And within the way it works is for all of the updates with the same timestamp, the order doesn't matter because there's no way to detect it. There's a second queue that keeps track of things that can be executed in the current instance. And the fundamental trick there is when you do a write to a variable, if there's something that's waiting on it, that might be in the future in the instant, but there may be other things that need to be done within that instant first. So that's what the second queue is for.
so I didn't understand it. You said it doesn't matter which order you do if they're on the same
So-
timestamp?
For the first priority queue that's doing scheduled variable updates.
And one says update the LED to 0, and the other one says update the LED to 1.
So
What do you
that
think?
won't happen. There's a mechanism for that.
Oh,
The issue more is update A at time 0, update B at time 0, update C at time 0, those, the order of that.
why can't update A to different values at the same timestamp happen?
Because I explicitly say you can't do that. And in fact, if you say do another update to a variable that already has an outstanding event on it, you blow away that event and replace it with your own. And you can do that because the execution of things within an instant is totally.
Okay.
That's partially for determinism, but partially also because I didn't want to do a malloc every time you schedule a new variable update. So the way it works is that each variable has space for one pending update. Yeah, so. The advantage of that is that it keeps it deterministic. The disadvantage is you can't put a big long thing into a buffer. What I'm thinking to do is relax that a little bit and say, okay, well, instead of just a scheduled variable that has a single update in the future, be able to say, okay, I want to be able to put 100 updates on this, but if I try to put 101, it would overflow. But like I said, I wanted to avoid malloc every time you do a scheduled update, which incidentally is what, yeah, think that's what happens in Verilog, for example. You should schedule an unbounded number of updates. Anyway, okay. The wait statement works a little bit like a condition variable. It hangs some little thing off the variable saying, I'm waiting on you, so that when you do a write to that, it schedules all those things. And that's what I just said.
I just worry about that first, in that you overwrite the. I mean, I could imagine you have something you do at certain intervals. You need to flip something.
Yeah.
Then it just happens that some other thing you do at some other irregular interval happens to happen at the same time as the other one.
No, it isn't by time, it's by variable. So
Yeah, but they're both doing something with the same variable.
If they're both trying to do something with the same variable, then you've got to take into account the fact that they're trying to do stuff with the same variable. You know, it's kind of like our discussion earlier about if you start up two blinks with exactly the same period, does it blink or not? There needs to be a definitive answer to that. And we can come up with different ways to do that. But
I just worry that it could sort of cause mysterious errors.
it probably could when two things are attacking the same thing. But my feeling is that when you're really doing a merge like that, you probably need to be a little bit more thoughtful about how you're merging that stuff anyway.
Maybe, yeah.
Yeah.
So I'm a little puzzled about this last line, when a variable is written, it's scheduled waiting code in a second queue.
Yeah.
So let's suppose that we wait on the variable and then we update it in the same instance.
Yes.
Okay, and the wait appears first in the code. What I previously understood is that
Right,
means it
right.
won't see the updates.
Yeah. So there should be an asterisk after this. What it actually does is it looks at the priorities of the things waiting compared to the priority of the current thing running, and only schedules things in the future. To avoid exactly this business of scheduling things in the past within the same instant. So you're right, this is more complicated than I described.
And the priority. What does that
The
mean?
priority is the syntactic order, basically.
Okay.
It's actually kind of fussy to configure, but yeah. Basically that, okay. Anyway, so we proposed a C API. The trick with this is that sort of the key thing is these waits. And the problem is that C doesn't like doing wait. C likes returning at the ends of functions. So you've got to do something. And the trick is to do something like wait, what you need to do is store your control state so that you can later be called again and get that restored. But then you also have to store all your local variables somewhere else. And so that's what all this stuff is about. You have to have explicit enter and so forth. Here's some stuff about the variable management. These are the things that are scheduled in the future. These triggers are the things that you have you use for the wait statements. They're the things that tell it to wake that up. And the problem is that a relatively simple program like this starts to look like this, or has to be coded like this in C. And maybe you can improve it a little bit. The last time I presented this, proto threads or something like that. And yeah, proto threads would fix 1, 2, 3, 4, 5 lines out of this mess. Anyway, I do not recommend this. This is more like the target for this is what a compiler should spit out as opposed to a human being should write.
So you would think that every par activity would require its own stack.
Yes,
But
yeah.
is that what's happening here?
Yes, so that's effectively what these enters are doing. And so because of the par, because it's not nested, you can't put the activation records on a stack. I'm putting them out in the heap. And so it makes a mess. And the thing is, even simple things like this is just an instantaneous assignment. You also have to point it to the activation record for the current thing. You have to write it in priority so that it knows what to wake up, and then you actually give it the value. It's just fussy. There's a lot of extra bookkeeping that you don't want a human programmer to have to fuss with. Okay, so we decided that stank, but that was never really the goal. The goal was to make that relatively fast, and then let's look at making the language palatable to something. Anyway, so this is where Robert comes in. So we developed this language, Scoria, which is a deeply embedded Haskell language, and you can see we have a variant of the after function here. This is the delay, the target variable, and the operation to perform, and we have out explicitly. And the things that should give you a hint of something weird is happening is we've got this routine thing that's playing with all the types and all the rest of it. And of course, this is all happening in the SSM monad. So definitely a step up above the C implementation. There's still weird stuff going on here and there to make it all work with the numbers, but you know, it's a start.
And implicit variables. Question mark.
So it's for,
Oh,
so the implicit ones are the ones we don't pass around at runtime. During compilation, this is deeply embedded, right? So this BLE object represents a larger thing that we don't really need to know about at runtime.
that's this bit. Honestly, I did not write this code, so I can't speak to it. So this is something that's fussed with it.
You can pass these around and you just get more parameters to your C functions. This is just the way we specify that.
Okay.
Yeah, so the BLE thing will not exist at when you run the, you know, this generated C code. But when generating the C code, we cannot pass it around in the Haskell framework. Pick out some stuff.
You cannot. I mean,
So what the BLE thing here is, it's essentially just a collection of other, you know, mutable variables. And when we,
But that aren't modified by the program or the story program
right,
itself, right? That's something outside. It's in the C world, right?
It's like calling a library function. You don't want to pass the library functions around to the C functions. Because you can just call them. We could have built that in the SSM mode and you wouldn't have seen this and you wouldn't have commented on them.
and I would have been happy.
Right, but now it's not. Anyone can add some with a new board, add new peripherals to it and have an implicit parameter that does it without changing the SSM on it. That's why we did it like this. I know you don't like implicit parameters, but we love them, Robert.
it's the one time I've used them. I think you told me about.
You don't support them in micro Haskell again.
Oh, no.
Anyway, so progress was made.
I should just interject that we have 10 more minutes for the room, but I checked and there's no booking after us, but
Okay.
so we know what the time is. Yeah.
Okay, yeah, no problem. Yeah, thanks much. Actually, yeah, I should say that. I mean, this is, you guys are great. You're asking all the questions that I hope you would. But of course, it's taking time. Okay, one of the things we did was implement it in full blast. The C version that I showed you earlier was actually just a simulation. It did not have interaction with the environment. This one actually has interaction with the environment. And the key trick here is that we're using the hardware timer. And then you looking at what time our program thinks it is, what the real time is, and then telling it to wake up appropriately. And so there's all kinds of really fussy stuff with semaphores to make sure that this thing all sort of plays in the right way. Input events don't go straight into our event queue, they go through another input queue so that they're admitted in sort of the right way and the right order and so forth. It's fussy, but it worked pretty well. Let's see. John Way, my PhD student, likes Lua, and it has continuations. So you can actually write it as a full blast library as opposed to the C thing with all these tricks. It begins to look quite a bit better. He also relaxed the syntactic control over ordering of parallel things and made it so that you can put in, I forget exactly, he had a mechanism where it would actually figure out these essentially priorities within an instant more dynamically. It's a clever algorithm. Not a big change in the semantics, but enough to be interesting. Let's see. Okay. Then finally, I'll get back to the RP 2040 that I was talking about to begin with. So like I say, these things are $1. Pair of ARM Cortex M0s, what I find hilarious on these things is that the processors themselves sort of shrink down nearly zero and it's all peripherals and so forth. That's a good thing. Pretty fast, 133 megahertz, over 256K of SRAM, QSPI flash, and this thing is like 2 megs on the I want to explain. Pretty good collection of GPIO pins. And the most interesting stuff for us are these two programmable IO blocks, which sit between the bus fabric and the GPIO stuff. And so in fact, we predict exactly. And I apologize for these drawings. I took them out of the Raspberry Pi documentation. Only idiots put little half circular jogs in the wires, but anyway. Okay,
It's so 1920s.
it is very 1920s, yes. I wish they'd use a 1920s font with it or something. I don't know. Okay. These things are fun. They are stored computers. They call them stored program computers. They call them state machines because they try to emphasize that they're very primitive. Each PIO has 4 independent state machines. They each share 32 instructions. This is not 32K of instructions. This is 1, 2, 3, 4, 31, 32 instructions. So very, very tiny. They are very primitive instructions. You've got jump, wait, in, out, very little else. The closest you have to arithmetic is decrement. And that's it.
And conditional jump.
And a conditional jump on 0, I think is about it. Very, very primitive. And yes, some fool has gone in and showed, oh, you can do multiplication of this. You can imagine how wickedly slow it is, but it is possible. We're not doing that. 4 32-bit registers. This is amazing. I thought the 6502 was stingy on the registers. This thing is at a whole nother level. Mostly because you can't directly access memory randomly in these things. So there's almost nothing you can do. The only reason to be interested in it is it's connected directly to the GPIO. So essentially 0 latency to get at the IO pins. And it's guaranteed single cycle execution. So unlike even the Cortex M0s, you can count cycles precisely with this thing, and it's guaranteed because there's no caching, there's no branch prediction, there's no one of these other unpredictable things. It's just happening, and with 32 instructions, yeah, access to is quick. So here's what we accomplished. A single PIO, we managed to cram in 32 instructions. Both the mechanism for time stamping events that come in. It's essentially a little loop that says, did the GPIO change? Did the GPIO change? And if it did, grab the new value of the GPIO, spit out the time stamp for that. And then actually a DMA mechanism copies it over into the event queue of the main system. The cool thing about this is we ran the clock of this thing at 128 megahertz, and we got it down to I think 16 cycles or something. I'm sorry, 8 cycles. The result is it's sampling at 16 megahertz. So yes, it'll miss things. If you have a 10 nanosecond pulse, it may or may not catch it. But 62 nanoseconds is a pretty good speed for hardware, especially on a $1 chip for software. Similarly,
Do you have a sort of clock out from this so that you externally can synchronize to where the edges are?
yeah, this is a problem. No, it won't do that. And in fact, one of the challenges is getting this timer synchronized with this timer synchronized with that timer. And because there's no way for this thing to go and read what the current time is outside, what we do is we very carefully start these two things up and make sure that they're synchronized appropriately. So that is a problem. And part of it is just, this is what we were stuck with the PIO. This is not my dream IO device, but we came reasonably close to it. The other end, this way to play even more tricks. But broadly what it is this thing, you tell it when you want the output to change, and you tell it what value it changes, and it actually triggers an internal interrupt that does it within exactly a cycle. So the interrupt latency on this thing is great, it's 1. Something like that. Anyway, the rest of this is pretty similar to what I showed you, what we did with the memo code stuff. But this is great. I like writing programs that you debug with an oscilloscope. So what this is this is an input from a button. And of course, it's not just a simple thing like that because buttons bounce. And so what this does is it waits for this event, and then as soon as possible tries to schedule an update on it. Now, this is a problem. It's not 0, it's 21 microseconds delay from input to output, and all of that is coming from, basically, that's all this stuff going on. Oh, plus this. So could be better, but could be a lot worse. Anyway, so one of the experiments we did for this 2023 paper, I should mention, so the authors on this 2023 paper are myself, John Hui, and Kyle Edwards, who is my 20-year-old son, who genuinely helped on this. He worked on the assembly language for it. He turned 20 that year, Mental Code turned 20 that year, and this is not an accident. He was born the first day of the first one, and I had to turn around and leave Mont Saint Michel and sit backwards, because he showed up 2 weeks early. So, violated real-time constraint. The experiment we did here was, okay, let's write a C program that goes as fast as possible and see how close we're coming to that. Well, what this does is look at an input and try to generate it out to the median. So it's in a really tight loop. You're basically doing nothing else. You're using an entire ARM core just to do this, which is kind of dumb. But we wanted to see how fast it could go. So the quickest we could get here was 1.8 microseconds as opposed to 13 for this particular one. So, the C beats us in latency. Not surprising, because it's all the endpoints. What's more interesting is this edge that I want to show you. And so what's actually going on here is we're looking for this input, and then we're saying, this is a pulse generator that's generating exactly a
20, it says that.
like a 50 microsecond pulse. Is that right? No, 100. Yeah, 100 microsecond pulse. And we're saying, okay, let's look for this edge, and then let's drop this thing 100 microseconds later. And this is where slang wins, and our environment wins. So here's the C falling edge. It shows up 1.4 microseconds late, and it is 960 milliseconds of jitter because of basically the phase in the loop, in the C loop that it captured it found the rising edge. This is slang. This is the beautiful part. It will start falling essentially exactly. So more or less, this is saying slang is as precise as our signal generator, which is digitally synthesized something or other that's doing it. This is jitter. But the important thing is here is 10 nanoseconds. So this is 62 nanoseconds of jitter. And that's exactly because we're sampling at 16 megahertz. And the external thing, maybe this is close to what you were asking, Leonard. The external function generator is operating at its own time. So it's not synchronized up to the same 16 megahertz thing. So I find this, basically we're right at the edge of, close to the edge of what the oscilloscope could easily give us. Certainly as precise as the signal generator that we're using. And it's matching the 16 megahertz. If you assume that you have a 16 megahertz clock, this is as close as you come with hardware either. So what this is testing how precise the input timestamp labeling is, which is basically dead on, and then how precise the output update time is, which also is basically dead on. And yes, it took us a while to figure out how to start these things in just the right way, but it was counting the counting the cycles ultimately was what it did, but in the end it worked.
And this is all because you have those PIO things that you can.
Yeah, we did some experiments like this with the earlier stuff with Scoria and so forth, and I don't remember the numbers of that, but of course they weren't sub-microsecond. It was we were talking about microsecond precision as opposed to nanosecond precision. Anyway, so. That's so the trick definitely is that these PIOs, they're not perfect, but they're remarkable for what they are. They're, like I say, they're tiny and they're just these funky little things that they decided to throw on the IP 2040. They were designed to speak weirdo serial protocols. Poster child are these WS 28. 26 or something like that. There are these RGB LED modules that take in a strange serial protocol where pulse width distinguishes ones and zeros. And there's no standard hardware that will do that, but it's a simple program to make the PIOs generate these waveforms of that kind of speed. The other thing that these PIOs have is input and output shift rate, which we're not doing anything with. But they're fun little things. Anyway, so the punchline of all of this is, so we got the timing precision that we were shooting for, which is kind of fun. The language isn't perfect, and the big flaws, and we've talked about a bunch of them, is the big flaws are PAR is kind of the wrong term here, right? It's not C.
No.
It's maybe pipe. Is it PAR or something like that? Concurrent or after or something like that? It's something of its own. I'm not entirely happy with the total ordering of instructions within an instant. It does solve the determinism problem plus some other things, but it's too draconian, and I'd really like to be able to get pure parallelism out of it somehow as well. Let's see, the latest and greatest thing, and Leonard, this is why we wanted to pester you. John is working on a version where he sort of adds SSM constructs, basically weight, PAR, and after into Haskell in your Haskell compiler, and then we're looking at, well, how does that affect the runtime to make that all work? And in fact, I think there's a lot of provocative ideas. I mentioned this earlier. This is not a great example of this, but the crucial thing is that this code needs to behave as executed at the time when it's first fired up. Because if LED changes later, well, you want to have some definitive rule about which version of that you pick up. And if you've got something mutable, and you've got to be careful about when you sample it. But if this was some long running thing that didn't have any side effects that only picked up immutable variables, then there should be all kinds of games you could play about. You've got a bunch of these after things running. When do you need the result? We know that because we know that things. Can we do earliest deadline first scheduling on that? And in fact, the laziness of Haskell makes that a provocative idea.
Sounds
Okay.
like a nightmare.
Yeah. Oh, it's probably a nightmare, but I think it's a paper. Most papers are nightmares. Okay, sorry, I'm way over time. I really appreciate all the comments and questions and so forth. Thank you very much.
Do we have any more questions? Yeah.
So one thing that I thought you were going to talk about was power consumption. I imagine that, when you have these weights, you can turn the clock off until the interrupt happens.
Right.
But then you showed us a system with your 16 resolution. I wonder, do you get good power consumption for that system, or are you basically running the clock flat out just to?
So
Okay.
I've not touched power because I've seen so many highly questionable studies on power consumption and so forth. So these things by themselves don't consume much power.
Right.
And aren't too bad. They're simple, stupid little things. And in fact, anytime you have put it to sleep, wait for an interrupt, you have something like that running anyway. Saying, oh,
Yeah.
did it change? So I'm not too concerned about these guys consume too much power because there's not much memory, there's the ALU, there is no ALU, there's like a decrementer, there's almost nothing, so that's not too bad. And sure enough, you could, when this thing knows it's scheduled something way in advance, you should be able to say, oh, don't do anything, just go to sleep and so forth. I've not tried to do those experiments or measure those values to figure out exactly what's going on.
Are you running on top of some small operating system?
No. Well, let's see. On the RP24, we were running bare metal. When we did the software Scoria, we were actually running on top of
Sephiroth.
well, we tried a variety of operating systems, right? Which
GPOS.
Yeah, one of them was really annoying.
I mean, it should be pretty easy to sleep while you're waiting for the timer interrupt.
Yeah, there's some issues about, I run into this daily. It's sort of like, am I going to have enough time for a nap before my alarm will wake me up? You run into the same thing here. You don't want to sleep the system knowing that you got to wake it up in 5 picoseconds. And so you do have to sort of look at it, decide, is it worth shutting down? I can't wake up in time, and do, depending on the wake up time, do I want to set the alarm a little early?
Scoria did that, right?
Something like that.
We experimented, but it was a bit tricky with the OS we used.
Because for IoT applications, you want to like sleep for a day,
Right.
and then
I don't think
Yeah.
we drew any conclusions on it, but we experimented.
Yeah, but yeah, no, certainly, and exactly the sparsity of this absolutely is, you should be able to set the thing to sleep for a day if need be, and just have a real-time clock running, which is very, very cheap power wise. But that wasn't sort of the main focus.
Any other questions?
Particular application area?
So, the original motivation for this actually was rats. Yeah, so I was contacted by a guy from Cold Spring Harbor that experimented on rats. And the time that it took them between when they heard a tone and when they stuck their nose in to get a little water reward was useful science. Now, you don't need 62 nanosecond precision to talk about rats, and with that kind of behavior, they're faster than us, but they're not that fast. Let's see, I've since lost contact with them, we ran out of money, blah, 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 so forth. It's a little frustrating, but something like that. So laboratory instrumentation. I do want to try the X-ray gun thing at some point. It'd be very interesting to see how can you actually prove that this is going to work. I think in certain cases, it shouldn't be too bad to say, okay, well, at the very least, we will generate this pulse of this length because we know that our output stuff. One problem with this is that we don't actually have a queue, we just have a single place buffer. And the reason for that is the semantics. If you say, do something in a minute, and then later say, oh, do something in a second, you override that thing that'll happen in a minute so that you can do something in a second. And you need some mechanism to be able, if you'd schedule that thing in a minute and it wouldn't let anything earlier go in, that would be a problem. So this should really be a priority queue, and at the moment it's just a single place buffer. There's funny little things in there.
All right, thanks.
Thanks.